Imagine a giant cloud of gas and dust floating in space. This isn't just any ordinary cloud. It's a vast, sprawling nebula stretching across light years. This cloud, called a nebula, was like a cosmic nursery, full of the ingredients to make stars and planets. Within its colorful swirls, new stars are born, and entire solar systems begin to take shape. Billions of years ago, our solar system was just such a nebula, cold and dark, but full of potential. Then, something incredible happened. A chain reaction was set in motion that would change everything. Maybe a nearby star exploded in a brilliant supernova, or a giant cloud of gas bumped into ours, sending shockwaves through the nebula. Whatever the cause, our nebula started to collapse in on itself. Gravity pulled the gas and dust inward, causing the cloud to shrink and condense. As it squeezed together, it got hotter and hotter and began to spin faster and faster. The spinning motion caused the material to flatten into a disk, with most of the mass gathering at the center. At the center of this swirling cloud, a star began to form, our very own sun. This young protostar was the heart of the new solar system. The more the cloud squeezed, the hotter and denser the sun became. The intense pressure caused nuclear fusion to start in its core. Eventually, the pressure and heat at its core became so intense that it ignited, bursting into life and flooding the surrounding space with light and heat. This ignition marked the birth of our sun, a beacon of energy that would sustain life on Earth billions of years later. While the sun was busy being born, the leftover gas and dust weren't just standing still. They were part of a grand cosmic dance, moving and swirling in the vastness of space. These particles were still swirling around the newborn sun, forming a flat disk called a protoplanetary disk. This disk was the nursery for the future planets. Imagine a pizza maker tossing dough in the air. It flattens out into a disk as it spins. Similarly, the protoplanetary disk spread out, creating a vast, spinning platter of cosmic material. This disk wasn't just a boring, flat pancake, though. It was a dynamic, ever-changing environment filled with swirling eddies and currents. It was filled with all sorts of leftover ingredients from the sun's formation, tiny bits of rock, ice, and gas. These materials were the building blocks of the future planets. Over millions of years, these tiny particles started to bump into each other. Each collision was a small step in the grand process of planet formation. As they collided, they stuck together like cosmic dust bunnies under your bed. These tiny collisions were the beginning of something much larger. These clumps grew bigger and bigger, their gravity pulling in even more material from the disk. Over time, they became massive enough to attract even more debris. These growing clumps would eventually become the planets we know and love. From tiny particles to massive planets, the birth of the planets was a slow but magnificent process. As these clumps of rock and ice grew larger, their gravity became stronger. Like cosmic vacuum cleaners, they sucked up more and more material from the protoplanetary disk. The bigger they got, the stronger their gravity became, and the faster they gobbled up nearby material. This process, called accretion, is how planets bulked up from dust grains to planet-sized objects. But it wasn't just a free-for-all. The sun's gravity also played a role, pulling material towards the center of the disk. This created a kind of cosmic tug-of-war, with the planets trying to hold onto their material while the sun tried to pull it away. This cosmic tug-of-war had a big impact on the types of planets that formed, influencing their size, composition, and even their orbits. Close to the sun, where it was incredibly hot, and the sun's gravity was strongest, only rocky materials could survive the intense conditions. These rocky materials clumped together over millions of years to form the four inner planets: Mercury, Venus, Earth, and Mars, each with its own unique characteristics. They're relatively small, dense worlds with solid surfaces, featuring mountains, valleys, and in Earth's case, vast oceans and life. Further out, beyond what we call the frost line, it was cold enough for ices like water, methane, and ammonia to exist in solid form. These ices, along with vast amounts of gas, were plentiful in the outer regions of the protoplanetary disk, creating a different environment for planet formation. This is where the gas giants, Jupiter, Saturn, Uranus, and Neptune, formed, growing to immense sizes by accumulating gas and ice. These massive planets are mostly made of gas and ice, with only small, rocky cores deep down inside, surrounded by thick atmospheres of hydrogen and helium. The stark contrast between the rocky inner planets and the gas giants of the outer solar system highlights the diverse conditions under which planets can form and evolve. Leftovers from lunch asteroids and icy wanderers. Not all the material in the protoplanetary disk ended up in planets. Between Mars and Jupiter lies the asteroid belt, a region populated by millions of rocky remnants from the solar system's formation. These asteroids are like cosmic leftovers, crumbs from the planet-forming feast. Further out, beyond Neptune, lie the Kuiper belt and the Oort cloud, vast and distant regions populated by icy bodies. These icy objects are like frozen time capsules, preserving the pristine materials from the early solar system. Sometimes, these icy wanderers are nudged out of their distant orbits and fall towards the Sun, becoming comets with their long, beautiful tails. The Sun turns on, light and heat flood the solar system. As the Sun continued to collapse and heat up, it eventually reached a critical temperature and pressure at its core. This triggered the most important event in the Sun's life, the ignition of nuclear fusion. Deep inside the Sun's core, hydrogen atoms began to fuse together, forming helium and releasing an incredible amount of energy in the process. This energy, in the form of light and heat, radiated outward from the Sun, flooding the entire solar system. The Sun's ignition had a profound impact on the planets. It blasted away any remaining gas and dust that hadn't been swept up by the planets, clearing out the inner solar system and shaping the planetary environments we see today. Once the planets had formed, you might think they would just settle into stable orbits and stay put. But the early solar system was a chaotic place, and the giant planets weren't content to stay in their original positions. According to a leading theory called the NICE model, the giant planets interacted with the remaining planetesimals in the outer solar system, causing their orbits to shift and change. These gravitational interactions caused a period of planetary migration, where the giant planets moved to their current positions. Jupiter, the largest planet, played a particularly important role, its immense gravity sculpting the asteroid belt and influencing the orbits of the other planets. Today, our solar system seems like a well-ordered place. The planets orbit the Sun in predictable paths, and the whole system appears to be in a state of equilibrium. But this stability is a delicate balancing act, a result of billions of years of gravitational interactions and a bit of cosmic luck. The planets are constantly tugging on each other with their gravity, and even small changes in their orbits could have dramatic consequences over long periods. The solar system is also constantly bombarded by asteroids, comets, and interstellar dust, reminders of the chaotic and dynamic nature of space. While our solar system may seem eternal, everything has a lifespan, even stars. The Sun, like all stars, is powered by nuclear fusion in its core, but the Sun's fuel supply is not infinite. In about 5 billion years, the Sun will run out of hydrogen fuel in its core. As this happens, the Sun will begin to change dramatically. It will swell up to become a red giant, engulfing the inner planets, including Earth. Eventually, the outer layers of the red giant will be blown away, leaving behind the Sun's core a small dense object called a white dwarf. The white dwarf will slowly cool and fade over billions of years, eventually becoming a cold, dark cinder. But even in death, the Sun will continue to influence its surroundings. The material blown off during the red giant phase will form a beautiful glowing cloud of gas and dust called a planetary nebula. This nebula will enrich the interstellar medium, seeding it with the heavy elements forged in the Sun's core. And so, the cycle begins anew. This enriched material will eventually become part of new stars and planets, carrying within it the legacy of our Sun and the possibility of life in distant corners of the galaxy.